Okay, let's get right into this one, because we spent a massive amount of time on this deep dive talking about the absolute giants, you know?
Oh, yeah, the massive ones.
Right, like GPT-4, Gemini Ultra, Claude Opus, the kind of models that basically require a small nuclear reactor to run and live in a server farm somewhere in Iowa.
Exactly.
But today, we are looking at the complete opposite end of the spectrum. We are diving into the small model revolution.
Which is, frankly, where some of the most fascinating engineering is happening right now. We're talking about Gemma today.
Right. Google DeepMind's new entry into the open weights arena. And before you, the listener, roll your eyes and think, oh, great, another 7B model to just clutter up Hugging Face.
Yeah, another one for the pile.
Exactly.
Yeah.
We really need to be clear about the pedigree here.
Yeah.
Because this isn't some weekend project. This is Google taking the architecture, like the actual research DNA of their flagship Gemini models, and distilling it down.
It really is. It's the same research, the same data curation techniques, and the same infrastructure. I mean, if you think of Gemini as a Formula One car, Gemma is basically the engine technology from that Formula One car, but repackaged for a vehicle you can actually park in your own driveway.
And that driveway, in this case, is literally your laptop.
Yep.
Or even your phone.
Yep.
And that's really the mission of our deep dive today. We aren't just going to rattle off benchmarks for you. We want to understand how Google managed to balance state-of-the-art performance with the very real constraints of running locally.
And we also need to look at why they decided to release the weights at all, you know, given their history of being pretty closed off with their top-tier models.
Exactly. It's a huge strategic pivot. But let's start with the hardware reality, the sizes. They released two specific versions of Gemma.
Right. A 7 billion parameter model and a 2 billion parameter model.
The 7B and the 2B. Now, for everyone listening who tracks this space, you probably know that 7B is sort of the standard size for a highly capable open model these days.
Sure, like LLaMA 2 or Mistral.
Right. It fits nicely on a standard consumer GPU. You can run it on a decent desktop. But the 2B, that's the number that really caught my eye.
Yeah, the 2B model is a completely different beast. It is explicitly designed for CPU and on-device deployment. That is the game changer here.
Because usually, I mean, when we get down to the 2 billion parameter range, we're firmly in toy model territory.
Whoa, absolutely.
They hallucinate constantly. They lose the thread of the conversation after 2 messages. They basically can't reason it at all. But Google is claiming this 2B model is actually usable for real, actual work.
And they have the data to back it up.
So how are they getting that kind of density? How is a 2B model this smart?
Well, it really comes down to the training data. Or rather the sheer unbelievable volume of it. The technical report states that these models were pre-trained on up to 6 trillion tokens of text.
Wait, 6 trillion. Let's just pause on that for a second. Because if you look at the standard scaling laws...
The chinchilla laws.
Right, the chinchilla laws that everyone in the industry cites. Those laws would suggest you don't need anywhere near 6 trillion tokens to train a 2 billion parameter model. They are vastly overtraining this thing, aren't they?
Precisely. And overtraining in this context is very much a feature, not a bug. How so? Well, the chinchilla laws tell you the mathematically optimal way to train a model if your only goal is to minimize your training compute. But Google doesn't care about minimizing training compute here.
Right, they have the compute.
Exactly. What they care about is inference performance.
Okay, so by feeding it way more tokens than mathematically necessary, like web docs, advanced math, raw code, they are essentially forcing the model to compress more intelligence into those few parameters.
That's a great way to put it. It's like, imagine studying for a final exam for 10,000 hours instead of just 100 hours.
Nah.
You aren't just trying to scrape a passing grade anymore. You know the material absolutely cold.
Right.
You invest all that compute up front during the training phase, which is obviously very expensive for Google, so that the end user gets a smarter, much faster model during inference, which is cheap for you on your laptop.
That makes total sense.
Yeah.
That 6 trillion token count is exactly why a 2B model can punch so far above its weight class. It's just totally saturated with information.
It is. And it's not just reading the dictionary one word at a time. We should mention the context window is 192 tokens.
Which, for a model this small, that's a pretty decent chunk of working memory.
It really is. It allows you to process fairly long documents, or you can maintain a pretty complex ongoing conversation without the model just forgetting what your initial prompt was.
But the token count is really just the fuel, right? We need to look under the hood at the engine itself, the architecture.
Let's do it.
So on a basic level, it's a standard decoder-only transformer. But Google being Google, they obviously didn't just grab the stock PyTorch implementation and call it a day.
No, definitely not. They made some very specific architectural tweaks, all derived from their Gemini research. And the first one, and this is super crucial for that 2B model we were just talking about, is multi-query attention, or MQA.
Okay, let's dig into MQA.
Oh.
Because this is rapidly becoming a standard trick for efficiency. Why does the 2B model specifically need this?
It's all about memory bandwidth. In a standard transformer architecture, for every single head of attention, you have to load a massive amount of memory keys and values.
Which takes time.
Right, it's slow, especially on a regular CPU or a mobile chip where your memory bandwidth is the primary bottleneck. Multi-query attention changes that by allowing the different model heads to actually share those keys and values.
So it massively reduces the memory overhead while it's generating the answer.
Drastically. It speeds up the generation of tokens to the point where if you want a model to feel snappy and responsive on a standard laptop, MQA is almost a hard requirement these days.
Okay, so that handles the speed. Then there's the embeddings. The report says they used rotary positional embeddings in every single layer.
Yes, and this is a pretty significant deviation from some of the older architectures that used absolute position embeddings.
Right, so instead of just stamping a token with a fixed tag that says, you are word number 5 in this sentence, RLHF does something much more complex with vector rotation.
Correct. It encodes the relative distance between the tokens.
Why is relative distance so important?
Well, think about tasks that require strict logic and structure, like writing code or solving mathematics. If I define a variable x at the very start of a Python function, and then I use it again 20 lines later.
The absolute position of that variable doesn't matter.
Exactly. The absolute position is irrelevant. What matters is the relative distance and the logical relationship between those two specific points in the code. RLHF handles that spatial relationship beautifully.
Which completely explains why we see such insane performance on those logic tasks, which we'll get to in a second. But first, what about GeGLU? I always read that and think it sounds like some kind of sci-fi super adhesive.
GeGLU, yeah, it stands for gated linear units. Basically, it replaces the standard RLU activation function, which you can think of as the basic on-off switch inside the artificial neurons.
Right.
Without getting too bogged down in the calculus of it, GeGLU just provides a much more complex, nonlinear flow of information through the network. It essentially gives the model a bit more raw expressive power per parameter.
Okay, so you combine the massive 6 trillion token dataset, the hyper-efficient multi-query attention, and these better GeGLU activation functions, and you get Gemma.
That's the recipe.
But we have to talk about the actual iron this was forged on, because they didn't train this on standard NVIDIA H100s, did they?
No, this is all homegrown Google Silicon. They use their TPU v5e chips. For the 7B model alone, they use 16 pods, which totals 496 chips.
That is just a staggering amount of compute.
Yep.
Over 4,000 specialized AI chips running full tilt. The energy consumption for that must have been immense.
It was substantial. The technical report estimates the emissions were around 131 tons of CO2 equivalent.
Wow.
To put that in perspective for you, that's roughly the lifetime emissions of about 10 average gas-powered cars.
But there's a caveat there in the report, right?
Yeah.
Google claims carbon neutrality.
Yes. Google's data centers operate under strict carbon-neutral commitments, utilizing a mix of renewable energy and carbon offsets. So, formally speaking, the net carbon footprint for training Gemma is calculated as 0. But the raw energy expenditure is undeniably massive. It really highlights this weird paradox in AI right now. The efficiency you experience at the user end on your phone
requires massive inefficiency and expenditure at the training end.
Exactly. That's the trade-off.
Burn the energy as a massive data center so my laptop battery doesn't die while I'm running the model locally.
You got it.
Okay, so let's talk about the results. We have this potent architectural cocktail. Does it actually work when you test it?
The short answer is yes. Very much yes. They compared Gemma directly to LLaMA 2 and Mistral, which are arguably the current kings of the open-weight hill, and Gemma outperformed similarly sized models on 11 out of 18 standard text-based tasks.
Now, 11 out of 18 is definitely a win, but it's not exactly a total blowout across the board. However, when you look at exactly where it won, that's where things get super interesting to me. It's the math and code scores.
Absolutely. On the GSM-8K benchmark, which tests multi-step mathematical reasoning and the math benchmark, Gemma outperformed its competitors by over 10 points.
10 points.
Yeah. In the benchmark world, a 10-point leap isn't a rounding error or a minor optimization. That is a full generational gap in capability.
And then there's the coding performance. This is the specific stat in the technical report that actually made me do a double take.
You're talking about the MBPP benchmark.
Right. The MBPP. They tested Gemma 7B, which I need to remind everyone listening is a general purpose model. It's meant for chatting, writing emails, whatever. They tested it against LLaMA 7B.
Which is a specialist.
Exactly. LLaMA was fine-tuned specifically on code. It literally lived and breathed GitHub repositories. And yet,
Gemma 7B scored 44.4%, while the specialized LLaMA 7B only scored 41.4%.
that is just wild to me. A generalist model walked in and beat a specialist on the specialist's own home turf. What does that actually tell us about the pre-training process?
Well, practically, it tells us that the 6 trillion tokens they used obviously included a massive, extremely high-quality distribution of code. But on a deeper level, it really validates a theory that's been gaining a lot of traction in AI research lately. Code is reasoning.
Okay, unpack that a bit.
Training a model heavily on code doesn't just make it a good Python programmer. Code is structured logic. So by learning to code, the model inherently becomes better at logic, better at strictly following complex instructions, and better at structuring coherent arguments.
So by making it a master coder, they basically inadvertently made it a better overall thinker.
Honestly, I wouldn't even say inadvertently. I think that was exactly their plan from day one.
Fair enough. It clearly worked. And just to cap off the performance section here, we have to mention MMLU, which is sort of the standard general knowledge test for these models.
Right. Gemma 7B hit 64.3% on MMLU. For context, that easily beats the LLaMA 2.7b model, which you'd expect. But it also beats the LLaMA 2.13b model.
So it's flat out outperforming a model that is nearly twice its physical size.
That is the very definition of efficiency. And it proves that parameter count alone is rapidly becoming a less useful metric for judging how smart an AI is. The architecture and the data density are the real metrics now.
Okay, so we have this brainiac model. It knows math, it knows code, it's super dense, but raw pre-trained intelligence is just that. It's raw.
Very raw.
It can be rude, it can be totally unsafe, it could just be weird and unpredictable. How did DeepMind actually tame it? We need to look at the tuning process.
Right. This is where the life cycle of the model shifts. We move from pre-training, which is basically just reading the whole library, to fine-tuning, which is learning how to actually have a conversation.
Right.
They use the industry standard 2-step process, supervised fine-tuning, or SFT, and then reinforcement learning from human feedback, RLHF.
SFT is basically just showing the model thousands of examples of good, structured conversations, right?
Yeah.
Like, user says hello, you say hi back.
Correct. They used a mix of synthetic data generated by bigger models and human-generated prompt response pairs. But the really interesting technical detail here is the formatting. They use very specific control tokens.
Yeah, I saw that in the report. Things like start of turn user and end off turn.
Yeah.
It almost looks like HTML tags when you read the raw text.
It does look like that, but functionally, it's all about probability steering. Remember, at its core, the model is just a fancy prediction engine.
Right, just guessing the next word.
Exactly. So these control tokens act as hard structural boundaries. When the model reads start of turn model, it literally shifts its internal mathematical state into generation mode. It knows it's time to speak.
And when it predicts the end off turn token,
It knows to immediately stop generating.
which prevents the model from just rambling on forever, or worse, hallucinating the user side of the reply, which used to happen all the time with older models.
Exactly. It takes the raw chaos of token probability and forces it into the neat, predictable back-and-forth structure of a human dialogue. And then, once that structure is set, RLHF comes in to polish the tone.
Right, the reward function.
Yeah, they use a reward model that's been trained on human preferences to subtly steer the model toward answers that are not just accurate, but helpful and safe.
Okay, speaking of safety, this is really the controversial part of the whole release, because Google has historically been the safety first, release later, or release never company.
Very true.
Releasing open weights feels like they are handing out loaded tools and just hoping people read the safety manual. How are they mitigating the very real risks here?
They operate under what they call a responsible release philosophy, and that starts way before the release ever happens.
Yeah.
They aggressively filtered the initial pre-training data.
So before the model even learned to speak.
Right. They ran heavy heuristic filters to scrub out personal identifiable information, or PII, and toxic content before the model ever even laid eyes on it.
But we know filters aren't perfect. We've all seen the crazy jailbreaks online where you trick the model into bypassing its safety training. Did they actively test for memorization? Because my biggest worry with open models is that it just verbatim memorized some poor person's social security number or private emails from a leaked dataset.
They took that very seriously. They conducted extensive automated attacks against Gemma specifically designed to force the model to regurgitate its training data. And the technical report claims they found absolutely no cases of memorized sensitive data.
Zero. I mean, that sounds almost statistically improbable for a model trained on a huge scrape of the internet.
It is a very bold claim. Now, to be fair to the researchers, they do qualify it in the text. They openly acknowledge that automated testing tools can have false positives and false negatives, and they might miss highly obscured data.
Sure.
But when they compared it directly to their older PaLM models, the memorization rate for Gemma was incredibly low. It heavily implies that their data deduplication and scrubbing techniques have gotten radically more advanced.
Okay, so let's assume the model itself isn't a walking privacy leak. What about malicious use? Because if I download Gemma right now, I have the weights. I can just strip out the safety filters. I can fine-tune it locally to write targeted malware or generate highly specific phishing campaigns. Google literally cannot stop me once the file is on my local hard drive.
And you've just highlighted the irreversibility problem of open weights.
It's a one-way street.
Completely. With a closed model like Gemini Pro, which you access via an API, Google retains full control. If they spot a vulnerability, they patch it on their servers. If you act maliciously, they revoke your API key in real time.
But with Gemma.
With Gemma, once those weights are out in the wild, they are out forever. You can't put the toothpaste back in the tube.
They do have a prohibited use policy attached to the download, but let's be real here. Hackers and bad actors are not exactly reading the terms of service before they write malware.
No, they certainly aren't. A use policy is a legal shield for the company, not a technical shield for the public. And to their credit, Google openly acknowledges this risk in the report.
So why do it? Why take the risk?
They are making a calculated bet. They argue that the overall benefit to the global scientific and developer community, having literally thousands of independent researchers examining the code, finding novel bugs, creating better safety techniques, far outweighs the localized risk of bad actors misusing a 7B model.
And let's be totally honest about the landscape, too. Bad actors already have unrestricted access to highly capable models like LLaMA 2 and Mistral.
Exactly.
Google isn't introducing a brand new, unprecedented danger to the world here. They are just entering an ecosystem that already exists.
Precisely. And by officially joining that open ecosystem, Google gets to influence it. They get a seat at the table to help set the global standards for how these smaller models are built, evaluated, and secured moving forward.
That makes a lot of sense. So, zooming out to look at the whole picture, we have a highly dense model that brings elite Gemini-level technology straight to local consumer devices. We have this massive overtraining strategy on 6 trillion tokens that results in off-the-charts math and reasoning skills. And we have Google, the king of the closed cloud, finally embracing the open weights ecosystem.
It really is a significant milestone for the industry. It strongly signals that the future of AI isn't just going to be monolithic, massive cloud models tightly controlled by 3 companies. It's going to be a hybrid ecosystem.
And that is the real aha moment for me in all of this. Because we've been so stuck in this mindset that AI is basically a utility service, like electricity. You rent it from a big tech company, you send your personal data up to their servers, they process it, and they send an answer back down.
A completely centralized model.
Right. But Gemma, and especially that hyper-efficient 2B version, suggests a totally different trajectory for the technology.
A trajectory where high-level intelligence actually lives at the edge, on your personal phone, integrated into your car, running natively on your work laptop without needing a Wi-Fi connection.
And that actually leads me to a pretty provocative thought I want to leave you, the listener, with today. Think about the scaling curves we just discussed. If these models keep getting exponentially more efficient, if a tiny 2B model today is just as capable as a massive 50B model was only 3 years ago, what happens in a few years when your phone has an onboard AI that is practically a genius?
It's coming faster than we think.
Right. An AI that knows everything about your life, your schedule, your files, but it literally never talks to the cloud. It's completely offline.
A totally private, pocket-sized superintelligence.
Exactly. But think about the economic implications of that. If you don't ever need to use Google search because the Gemma model running locally on your phone already knows the answer and just tells you, Google might have just disrupted its own core business model to stay relevant in the AI race.
That is the ultimate irony, isn't it?
It really is. Are we potentially looking at the death of the ad-supported cloud-based internet, and it's being killed by the exact same big tech companies that built it in the first place.
That is the multi-billion-dollar question everyone in Silicon Valley is trying to figure out right now.
It is definitely something to mull over while you go download the Gemma weights to your laptop. Thank you for joining us on this deep dive. We will catch you on the next one.